Testing. Okay. Hopefully. Okay, great. Good afternoon, Patrick. And welcome to another in the series of advanced lectures for Prolog Essentials. Today we're talking about constraint handling rules. And I'm going to go over some of the basics of CHR. How many of you here have had time to look at the CHR material at all? Let's see a show of hands here. And forgive me, if you're going to have me get up at 2 a.m. and do lectures, I'm going to sip tea. Okay, great, Chandra. Glad to see you guys hanging in there. No chance yet. Very behind. Yeah, it's hard to keep up. Okay. Everybody's, yeah. Okay, great. One or two folks. Okay, constraint handling rules are a paradigm for computing, actually, that has been developed over around Tom Fruworth and a large number of other researchers as an interesting way of dealing with a number of issues, including the state. So the basic idea of constraint handling rules is that you have a constraint store, which you can think of as a box. And in that box you have constraints. And then you have rules. So here, for example, is what we would call a propagation rule. When there's a green diamond and a red heart in the store, add a yellow sun. So let's see how that works in practice. Here we have an empty store. We put in a green diamond and nothing happens. We put in a red heart, and this time the rule fires because we now have everything on the left side of the rule. I will go back and refresh you about the rule. There's the rule, and so the rule fires and the yellow sun gets added. And now no more rules fire, and we're back to this so-called solved state. That's generally what happens. You call, and from Prolog, if you make a constraint, then you can just call it as a Prolog goal, And when you do, it gets added to the store. And then the store, all of the rules apply until no more rules can apply. And the store becomes quiet again. Okay, that rule was a propagation rule. There are 3 kinds. The rule for idling, is it instantaneous or is there a delay? It is instantaneous. I mean, basically when you call to add something to the store, that call won't return until the store becomes quiet again. All of this happens in the thread in which you called the store. If one rule removes and then another rule adds it, it's going to take the topmost rule it encounters and run that rule. And then after it runs that rule, it'll start all the way up at the top, and it will look downwards until it can find a rule that it will fire. Now, if you have a rule, once it has fired for a set of constraints, it's not, when we go back up to the top again, it's not going to fire for that combination of constraints again. And I'm going to show the get foo pattern a little later in this lecture, and that get foo pattern is will demonstrate that. So there's a section called Which Rule Fires in the CHR tutorial. I suggest you refer to that as well. Okay, a second type of rule. This is fine for adding things to the store, but we probably want to take them out sometimes. A simplification store lists some things. A flower and a heart, when they're both... rule ordering is in the source is important, yes. So when you have a flower and a heart in the store, replace them with a cross. This is a simplification rule because it removes the things that are required to be in the store for the rule to fire. I'm going to check and make certain that's true. That's happening properly. Okay. So here's our simplification rule firing. From Prolog, we will add the flower, and then the rule will fire. And that will remove the flower and the heart, and we'll add the cross. However, remember, you might want to do both things. You might want to leave some things and retain others. So let's have a third rule, a so-called Simpagation Rule. When there is a stop sign and a heart in the store, replace the stop sign with a flower. So we're going to remove the stop sign and add the flower. The heart is going to remain. Now, notice I said with the exact same constraints. This actually makes Simpagation slightly different than simply re-adding the heart, than using simplification and then re-adding the heart as well as the flower. Was that clear to everybody? Should I go through that again? There's a difference because when you take the heart out of the store and then put it back, then we get back into Chandra's question, and we get it back into the fact that we now have a new constraint in the store and more rules may fire. Okay, so Prolog adds a heart. No. Okay. Let's go back. All right. Okay. The source ordering is important. So the rule is that, or the way it works is that rules will only fire once on exactly the same set of constraints. Otherwise, for example, if you had a propagation rule, consider our first rule. Here, our very first rule, we had a diamond and a heart, and we had a sun. Well, now here's the final state of that one. But now we still have a diamond and a heart. So maybe we should add a second sun, and then a third sun, and then a fourth, and so on to infinity. But no, the rule will only apply once for exactly this diamond and exactly that heart. If I do something to put a second heart in, I will get a second sun, because it's a different combination of constraints. And I see you typing. I'm going to wait. And slurp at you. And I see you typing Simpagation. Okay. Now, Simpagation. So Simpagation takes some of the constraints that have to be present for the rule to fire and removes them. And you can control which ones. In this case, the stop sign is going to be removed, but the heart will remain. So we can replace the stop sign with flower. And again, this is important for what gets activated. It's the same heart. Another way of doing this would be to use a simplification rule and say when you see a stop sign and a heart, remove them and put in a heart and a flower. But of course, if you do that, you've reactivated the heart. Yes, that's why they are not exactly the same. Simpagation is not the sum of simplification and propagation. That's not the same as simplification, where you put back a copy of the constraints, because they're not exactly the same constraint. They're a different copy of the same kind of constraint. Simpagation is an atomic operation, yes. And simpagation is and it does not remove the heart and re-add it. It just leaves it there, because adding something to the store is a special thing that causes things to happen. Is that clearer? Forgive me looking off to the side all the time, but that's where your questions are. Okay, great. So we're on to Simpagation. Let's watch it do Simpagation. We'll add a heart. This was our previous state. We add a heart. We add a stop sign. And that causes the rule to fire. The stop sign gets removed. The flower gets added. This is the new state. But hey, remember this other rule? Our simplification rule? That rule can now fire. So it's going to fire. The flower just got added, so this rule gets activated because it's going to delete the heart and the flower and add a cross. So that's our final state. So those are the three kinds of rules: propagation, simplification, and simpagation. And this is closer to the CHR syntax. This arrow is propagation. This is simplification. And this with the backslash is simpagation. And it's the material between the backslash and the double-headed arrow that gets discarded. I will tell you that I always have trouble remembering those, and for a long time had a sticky note with those on them. Are the two stop signs identical? If I take two pieces of paper out of my printer, they're pretty much identical. I mean, if I held them behind my back and then brought them out, you'd be hard-pressed to tell which one I originally had in my left hand. If there is a rule to remove one stop sign, which one would it remove? One of the stop signs must be active, and that will be the leftmost one that is matched. So it will remove the old one. This can actually be important. Suppose that these have arguments, then this would be how you would update. Suppose I'm carrying a single global value, and when I add a new global value, I have a Simpagation rule that says if I have two global values, only retain, I could just put true over here, and then have, foo, foo of x and foo of underscore and foo underscore. I'll just modify the slide. I should have done that in the first place. Propagation, simplification, and Simpagation. Okay? So, Chandra, yeah, like I say, if I wanted to update a single global value, I could remove the other copies by using a Simpagation rule, and it would do what we expect. It would keep the newer one. And I'm waiting for folks to finish typing questions. Josh, yes, CHR is not Prolog, and in fact, I will warn you that because it looks so much like Prolog, it can be easy to get trapped, to get tripped up by assuming you're in Prolog and thinking you're in Prolog. So yes, it's much like having a regex in Java. You know, you're in a different language, and now backtracking. If you wish to, on the right-hand side, you can call a Prolog goal. And if you call Prolog goals as part of the right-hand side, you will, you may generate choice points. Those choice points do propagate back. So if when I add the green flower from Prolog, it sets off a rule, and that rule calls some Prolog that leaves a choice point, then that choice point will appear when I get back from the call to add the green flower. Is that sieves that interact. Okay. Hang on. Even firing is more the idea of keeping states managed, and one can can one backtrack? Yes, one can backtrack because, well, okay, let's see here. You cannot backtrack in CHR. CHR is not Prolog. You can fail, and if you fail on the right-hand side, for example, you call some Prolog that fails, then the original attempt to add the constraint will fail, and the state of the store will be unchanged. Now, Patrick, for Simpagation, I missed this part. Can either the heart or the stop sign be converted into the flower? No. For Simpagation, the rule is take, I'm going to use as my example this particular rule. The semantics of this are that everything to the left, and there could be several of them, comma separated, it remains. And then everything to the right of the backslash, and there could be several of them, is removed. Everything after the operator, after the double-headed arrow, is actually look through, and it's usually a sequence, it's a comma separated sequence of Prolog terms and CHR constraints. If they're CHR constraints, they are added just as if you called them for Prolog, and if they are Prolog terms, they are called. There is one bit of syntax that I did not intend to cover in this lecture, and that is immediately after the operator, you can place a Prolog term, which will be called as goal, and this is a so-called guard. And the rule will only fire if the guard succeeds. So, for example, if I want to replace, let's say I'm keeping track of the maximum of a value. And so when I add, imagine I have, tell you what, I'm going to duplicate this slide so I don't mess up my slide deck. And forgive me, I'm going to do some live slide making in this lecture. Some people do live coding. I do live slide making. And then so I'll give this a variable, and then I could come out here and say x greater than y, or bar, and then move my flower over. And of course these have periods at the end. Now I'm only going to keep the largest one. So later I can go back and look and see what value I have in the heart, and that will be my biggest heart. And whoops, what I really want to do here is I don't want to add anything. I'm just going to get rid of the smaller of the two. And so I can just say true here. What if a guard succeeds, has a choice point? A guard should not have a choice point because a guard should not bind variables. That's a rule. You are not allowed to do something like this. The compiler will yell at you, and it's a no-no. You are allowed to do this, because this one's in the body. You are also, and in fact, if you, what will happen if one of these is not instantiated is that it will actually wait on you. it will block execution, and this roll will kind of be left hanging until you bind the variables, and then at that point it will either fire or not. This characteristic actually allows you to build constraint systems to kind of decorate variables, and we will get into that more next week. Okay. You guys are doing great, asking lots of great questions tonight. I'm really happy about it. X equal 3 is simply Prolog. That's just some Prolog in the body. And we'll unify x with 3. So x will have to be 3. That's normal Prolog. So you're going to say x equal 3. Okay. Here you are asking, can it unify to 3? Well, the problem is that now you have forced unification. And in fact, yeah, actually, I may have typed equal when I probably should have said that x. Yes, the system will wait. It does this only for certain operations, and in fact, I'm actually incorrect that it will do that for equals. It will do it for ground. I could say here, ground but what you're not allowed to do is to ground variables. So if you call this, yeah, hang on, I have flubbed up here, and you should not do this. That will instantiate a variable. However, if you do this, now you may wait. Ground will wait. My apologies. Does the guard clause apply to simplification and propagation as well as simpagation? Yes, they work identically. If not, what's the... no, it applies to all three of them. Okay, I'm going to keep talking. If don't let that inhibit asking questions, I'll pop back and keep talking if I haven't put questions to rest. Yikes! State! Okay, question for you. Why is state bad? Why is state problem? I think Tom Armstrong called state part of the awkward squad. So, why is state bad? Let's hear from our audience. And like I say, I didn't want to cut off questions, but it seemed we were done. So, why is state bad? Somebody tell me. Some of you must be types or get the fuck out. Functional programmers and hate state. State causes mutations, side effects, and complexity. Boy, that's a... Yeah, keeping state in your head. Josh's explanation is the when you start mutating things, you have concurrency issues. Yes, it's poor for concurrency and parallelism. Yeah. So, concurrency is much more difficult with mutable state. And Chandra, yeah, I think everybody agrees that state is always an awkward part. Well, Chandra, if it's immutable, you don't have state. Okay. Josh says it causes side effects. Yeah, the truth is it has bad mathematics. Okay. State is bad. State is bad for concurrency. State is bad because you change things in one place and it's hard to keep everything in sync. And state invariably is hard to reason about. So people have done various things to avoid state or handle state. The first is objects, and on the EU time we had Norbert in here. Norbert's a big small talk guy, and so that turns your state into a model, and then you can have a model and a view, and so that handles to some extent this issue of complexity and of keeping things in sync. I've been programming a long time, and programmed desktop applications before there were objects. And one thing we always had was lots of bugs where views didn't get updated. And then object-oriented programming came along, and that became much easier. Okay. It doesn't cure the thread problem by any means, but at least now we have encapsulating methods, and the methods can do things like do synchronized and avoid some of the thread problem, but of course you're still dealing with locking, with deadlock. However, objects end up with another problem, and that is that pretty soon you end up with all these crazy crisscross connections between objects, and that becomes really hard to understand. So people say, well, we can separate that back out by inversion of control. And inversion of control, it sounds like a fine idea until you actually try and do it. And I think most people who will have used an inversion of control system will tell you quite often awkward as heck. Okay, ways to avoid state. Another way to avoid state, use agents. I used to program in an agent language. I ran a large virtual world education program, and using the same tech we're using for the class, OpenSim, and it has a scripting language, and that is an agent language. So it's So, for example, if you go down and so if you go to any of the stuff that kind of dynamically works in the world, that's all run by agent-driven systems. Each of the little scripts in the agent system has its own thread and communicates solely by messages passed in and out and placed on queues. So that really solves the thread problem. It's impossible to make a deadlock in LSL. You can sort of demonstrate one, but you can wait forever for a message, but that's actually what's technically live lock. It's also quite decoupled, and in fact, the virtual world's a good example of this. You have all kinds of things that could come along and happen, and so, for example, there's a bunch of robots that turn and look at you, and those robots just sit there and query the environment. They scan looking for avatars near them and then turn around. And that's a pretty decoupled process. It has its downside. It's very hard to make kind of verb objects. I built a little constraint handling rule demo with some robots that implement a couple of simple rules, and those things were surprisingly hard to code because they had to kind of keep track of, oh, I have seen a red box and a yellow box, and that's actually hard to do in an agent language. A verb object. A verb object is an object that represents something going on or something or an action. So Rich Hickey calls Clojure the revenge of the verbs. We will have objects like a connection. Well, a connection is a thing that's doing. We have an object that represents a thread, or an object that represents suppose I want to do a series of, imagine I'm in Java and I want to do a federated query, where I'm going to go out and call 3 different servers, and I'll use the results from the first one as parameters to the second query, and then results from the second query as parameters to the third query. Well, I've got to keep some state there because I'm going to be doing the HTTP calls, and I will have I/O going on, and I will wait for the remote server. So that's a verb object. JavaScript's actually pretty good with verb objects because you have lots of callbacks, and you have wait. So that's one other way of avoiding state is with an agent-driven language. Then we have functional programming, and we have monads. This certainly avoids state, but when you're working with them, it can feel more like this is a way of sweeping state under the rug. And in fact, a monad is just a fancy way of dragging all the state along with you on the stack, which of course is what we usually do in Prolog. You know, sometimes functional programming methods of dealing with state are more painful. So one of the things I like about CHR is that instead of kind of like going, oh, no state, no state, no state, I don't want no state, it happily embraces the fact that we want to think about how things change in the world. Each CHR store is single-threaded. It's associated with the thread you're on. And if you have multiple threads, you get multiple stores. And however, CHR evaluation itself is often concurrent. And CHR can be evaluated in a highly concurrent way and can be automatically parallelized, and there are lots of academic papers about parallelizing CHR evaluation. Okay. All right. More questions before I go on. All right. And that's an interesting. I deleted that, but it was. This is an interesting example of some of the complexities of dealing with state. I occasionally get debug messages from rampaging robots because, of course, when the robots leave their area, they're deleted by deleter things that scan for robots in the area and then kill them. And every so often, and there are multiple of them and they overlap. They're the big red cubes that if you look over the wall, you can see. Those things have a spherical zone of search, and the spheres overlap, and occasionally two of them will see a robot at the same time. One of them will delete it, and then the other one, when it goes to try and delete it, the object's no longer in the universe. Whoops. Am I there? I am. I think I'm fine. All right. Okay, so I want to talk about getting things back out of the store. This is a pattern called the get foo pattern. So I want to get something, traditionally foo. I have a bunch of foo1 constraints. They have arguments, and I want to get them, and I want to get a list of the arguments. So we have some constraints. This is how you define constraints. For those who've not yet started the CHR constraint, the CHR module, use library, of course, and then you say CHR constraint, this is directive, CHR constraint, you define foo, of course, as a constraint, and then we're going to define one foo. And one foo is just a single foo, so we're going to use it to make copies. And then we have to have get foo, which is the original thing we add to the constraint store to get our value back, and then we're going to need this collect foo for something to temporarily hold the list. Okay, and now I will add things to the store. You can add things to the store just by calling them from Prolog. So here we are adding 3 foo constraints with 3 different values. All right. So I said I added 3. My examples here have 4 of them. A little bit out of sync there, but okay, so there's my 4 foos. And now from Prolog, I will put in a get foo. And it has an unbound variable. And we're hoping that unbound variable gets bound to the list 1, 2, 3, 4. Okay. Our strategy is I'm going to collect these things. So I'm going to destroy them as I collect them. So I know I've done that. And if you destroy them as you collect them, then it's important that you don't destroy the original ones if you want them to remain in the store. So the first step is to make a duplicate. So I will make a rule, a propagation rule, that says if there's a foo constraint in the store and get foo is there, right at the end, by the end, we'll have removed get foo. Then add a 1 foo. Okay, and that will happen for every foo in the store. So I will get copies of them 1, 2, 3, and 4 as 1 foos. The next step is that I am going to replace get foo. Notice there's no purple cube at this next stage. I am going to replace get foo. Hang on, I will zoom in here. And by the way, this thing's back behind the CHR. It's one of your assignments to go visit it. This thing's back behind JWU. There's like a subway tube off to the left near the DIKW pyramids. If you head over that way, there's a ramp. I will warn you, the ramp's like not a very convenient way to get over there. I suggest you fly. Okay, but back to the subject at hand. The next thing I'm going to do after I have duplicated is I'm going to get rid of get foo. Notice that I'm hanging on to the variable. I'm going to make a collect foo that has the same variable. Okay, so that way I know kind of which phase of the process I'm in. Collect foo then is going to be added to the store, and that actually should just say X, by the way. And then now, if I have a 1 foo and a collect foo, then I am going to remove them both. Notice this is a simplification object. Are people, give me some feedback here. Are people following along? Is life good? Okay, I have a 1 foo and a collect foo. I'm going to delete them both. And then I'm going to make a new list. And this is a new variable, L1. It's not bound to anything. So I'm going to put the X in the head of the list. And now I have a hole in the end. This is the traditional hole list pattern. And now I'm going to add a collect foo with L1 in it. And I see people typing, so I'm going to stop, see what people have to say. Okay, yeah, revisit the, you know, you can come down here and look at this anytime, and check it out in the get foo is well covered in the DCG tutorial. Okay, so the next thing that will happen is I've got a one foo and a collect foo. It's going to build this list up, and here it keeps munching away. This list, of course, this was originally 1 back here with a hole, and now that hole gets filled with the list 2 and a hole, and the hole gets filled with 3 and a hole, and we keep deleting the one foos, and finally we get down to where there are no more one foos, but there's a list with a hole in collect foo. And at that point, now this rule won't fire because there's no one foo, so that lets the next rule fire. And this is why ordering is important, is because you can hide rules this way. And now we're going to hide this. Now you're probably thinking, why didn't you just say true, Annie, and put square brackets over here? That's because we're in CHR, not in Prolog, and collect foo with an unbound variable is different than collect foo with a pair of square brackets, and we would not have fired the rule. So we want to do the binding on the right-hand side. You basically never want to unify except on the right-hand side. All right? But when we do that, it's going to convert it to a normal list. This, of course, is tied by unification all the way back out, and this will get returned to Prolog. So that is the get foo pattern. And yeah, it's a little bit of hand waving. And and bizarrely, it was not documented anywhere, and nobody had said how to do it. And I will be eternally grateful to Alan Balju for kind of demoing it in a way. So I think I named get foo. Realizing it was something that was a pattern that people would need. Okay. And I think that's good for tonight. For this afternoon, for those of you in the U.S. I invite you to come down to the museum. There's a fun demo over here. Where you can play around with adding constraints to a store. And the robots act as rules. And otherwise, I think we're good. Thank you for coming. And we got a nice establishing shot to go out with. Here's the Museum of Constraint Handling Rules. Okay. Questions? Comments? Otherwise, I'm seeing people typing. Yeah, I can do that. Let's see. Hang on. Yeah, Josh, this is a pattern called a whole list. You keep you make a list with an unbound variable as its only element, and then at the next stage you unify that unbound element with a list with something and an unbound element, and then you make your recursive or whatever call, and you pass it both, and you pass it the unbound element, and then this gives you access to the tail of a list. This is a way of building lists from the end rather than from the beginning. Of course, you can pass the beginning as well, and now you can add things to either end. Yeah, this is called difference lists. If you'll remember the assignment to watch Sparrows and Eagles, Marcus Triska covers difference lists quite well, I thought, in that. So if you're confused by all this, you might go back and have another peek at Sparrows on Eagles. The CHR stuff is neat. By the way, it's been implemented for many languages. Obviously, it's a different language than Prolog, and it's most commonly embedded in Prolog, but it could be in any language. So CHR is interesting. And I'm finding myself writing more and more CHR with my Prolog as time goes by. Okay, I think that ends the questions, so I will let you all go. And somebody has posted something on random. I'll go look at that. Then I'm back to bed because I have to get up in the morning and move. Yeah, it's another brain-twisting domain. Okay, I'm going to get off the stream. I'll answer questions on chat.